We discussed the quasi-harmonic approximation earlier. In the quasi-harmonic approximation, the free energy contribution due to vibrations is calculated using that formula, which contains temperature, of course, and vibrational frequencies omega lambda. The essence of the quasi-harmonic approximation is that that expression does depend on the geometry of the crystal, because vibrational frequencies can be calculated at various uh, shapes and sizes of the unit cell. Therefore, if one adds vibrational free energy contribution to the density functional theory energy, the calculated this way free energy would depend on crystal geometry parameters and the temperature. And therefore, optimizing the free energy with respect to those parameters would allow us to calculate geometry of the crystal at different temperatures as a function of temperature. In other words, to consider crystal expansion, for instance, as a function of temperature, as well as the dependence of vibrational frequencies on temperature as well. So this is all within the quasi-harmonic picture. This is a full quasi-harmonic picture. There is also simplified or naive quasi-harmonic approximation, in which vibrational frequencies are calculated at zero temperature, at the geometry which gives the minimum to the density functional theory energy. And then this expression is used with fixed vibrational frequency to give rise to the dependence of the free energy on temperature and geometry of the crystal. So now I will consider a few examples of the usage of the quasi-harmonic approximation in its trivial variant and in the full variant. The first example is that paper here, in which a transition from one phase on the surface of calcite to another phase of simple molecules was considered. These are the molecules. I won't discuss with you the whole paper. Is rather long, and the whole story is fascinating. But what I would like simply to show here, just to illustrate the quasi-harmonic approximation, two gas phases on the surface were considered in this paper: the phase of dimers and the phase of monomers. In both phases, the dimers and monomers, they can freely move around the surface. And in order to calculate the total free energy of either of these two systems, one can calculate the DFT energy, then add the vibrational contribution via the quasi-harmonic approximation, and also add a configurational entropy term associated with the fact that one can distribute a certain number of molecules or monomers on the lattice sides in various ways. And here you can see the dependence of the free energy for dimers and for monomers, and also some other phases, crystalline phases, which were calculated in this paper as a function of temperature. So in this case, a trivial implementation of a quasi-harmonic approximation was used, but a similar approach of naive quasi-harmonic approximation or trivial quasi-harmonic approximation was attempted in this paper. It was about 20 years ago, where they considered a phase transition from alpha-tene to beta-tene. So this is alpha-tene, which is FCC diamond structure, and this is beta-tene, body-centered tetragonal structure. And the phase transition happens here at a temperature around 300 K, yes. This is called TC. So it's 13 Celsius, exactly, to be exact. And they explained the phase transition exclusively by the change of the vibrational structure of this system. So here you can see dispersion curves for alpha-tene of the vibrations. You see acoustic branches, you see optical branches here, and The same for the beta teen. And if you look at the order of magnitudes of the vibrations of the alpha teen have higher frequencies. So here you have a density of states for beta teen. It ends somewhere here, and alpha teen has a huge vibrations around 200 inverse centimeters. Correspondingly, if you calculate the contribution to the free energy of these vibrations, it appears that because of these higher frequencies for the alpha teen, the entropic contribution to the vibrational free energy for the beta teen is much larger than for the alpha teen. And because the entropy comes into the free energy with a minus sign, then the free energy of the beta teen at some point becomes lower than the free energy of the alpha teen. And indeed, if they plot it here, you can see the free energies of alpha and beta teen. And at that point here, around 300, just over 300K, they cross. And if before that temperature, alpha teen has lower free energy, as it should, yeah. After that temperature, beta teen has a lower free energy, so it is the most favorable structure. So here in this paper, they also use naive quasi-harmonic approximation. So only once at zero temperature, the vibrational calculation was performed, and then vibrational frequency was fixed, and the free energy was calculated at different temperatures. However, in this paper, this is the reference here, a rather careful analysis of the phonostructure and the free energies of a number of compounds was made. And in this case, they performed a very thorough investigation in which not only a quasi-harmonic approximation was fully used, so in other words, the structure was considered at different crystal volumes, and therefore vibrational frequencies were calculated at different lattice sizes. But they have also added contributions of unharmonicity to the calculation, of possible defects. The electronic contribution to the free energy was also considered. They performed a very careful analysis of the K points convergence, took a very large supercell to account for more K points of phonons in the brilliant zone, and so on and so forth. And they calculated the thermal expansion for different systems, comparing different methods, which are shown here. And agreement with experiment, which is shown by dots here, is quite impressive.